So we have divided this particular chapter into 3 modules. In the first module, we'll be talking about theories of acids and bases and what are the different factors which will decide the strengths of acids and bases. Bases will be doing in the next module. The aim and objective of this particular chapter is to understand various ways by which acids and bases are classified, then understand the relation of pH, pOH with pKa, pKb, effect of temperature on pKa, pKb, comparative aspects of strengths of acids and bases, and various reactions where acid and base acts as a catalyst. Before we enter and understand these theories, let us see one video. In this video, we are talking about history of acids. Fascinating journey of defining acids and bases done by various scientists. So there are 3 important theories we are going to discuss now in this theories of acids and bases. The first time very nicely tried to categorize scientifically various compounds as acids bases was done by Arrhenius. Savante Arrhenius introduced his theory in 1884. So Arrhenius theory says that acids are the substances which, when dissolved in water, produce H plus ion, or they increase the concentration of hydronium ion. For example, if HA is any acid, if dissolved in water, produces hydronium ion. For example, acetic acid dissolves in water and its H plus ion increases, reacts with water to produce hydronium ion. Similarly, as per this particular theory, base is a substance which ionizes, dissociates in water to produce hydroxyl ion, that is OH minus ion. So this is how, in general, BOH is any Arrhenius base which dissolves in water to give OH minus, that is hydroxyl ions. For example, NaOH, which is a strong base, ionizes to give hydroxyl ions. Or they say that when I put litmus paper in acid, what happens to the litmus paper? The blue becomes red, then it is called as acid. And if I put my red litmus paper in base solution, then it will be turning to blue. Another theory was introduced was by Lowery Bronstead, and this theory was introduced to explain various atoms, ions, molecules can be classified as acids and bases by this theory, and it is called as proton donor acceptor theory. Now they have given little wider definitions of these acids and bases. As per this particular theory, An acid is the substance, it can be species, it can be ion, which will donate hydrogen cation, that is H plus cation. We also call it as proton. And base is the substance or a species which has the ability to accept H plus ion. So therefore, we have named this particular theory as proton donor acceptor theory. Now, this particular theory is not restricted to solvent water, first of all, which was a problem with Arrhenius theory, that your substance should be dissolved in water and then only its property will tell whether it is acid or base. Along with that, Lowery and Bronstead introduced the concept of conjugate acids and bases. If a compound is to behave as an acid by donating proton, then there must be some base which will accept the proton. And therefore, what they say that acid reacts with base to produce a new pair of acid and base. We call them as conjugate acid-base pair. So, if HA is any acid which is going to donate proton to base B, then I will get A minus Nn and BH plus cation. Now what you will find that BH plus and B are conjugate acid-base pairs of each other, and HA and A minus are conjugate acid-base pairs of each other. What is the difference between them? So you'll find that an acid and its conjugate base, they have difference of one hydrogen. Similarly, a base and a conjugate base, they have a difference of one hydrogen. So such kind of pairs are called as conjugate acid-base pair. For example, acetic acid and acetate anion. You'll find that they have a difference of one proton, and this is a first conjugate acid-base pair. Similarly, H2O and H3O plus, there is a difference of one proton. This is another conjugate acid-base pair. So, acid donates proton to the base, base accepts the proton and gets converted into its conjugate acid, whereas acid is converted into its conjugate base. So this is how they say that whenever acid and base react with each other, they produce a new pair of acid and base. We call them as conjugate acid-base pairs. Let us check what is this conjugate acid-base. So I've got list of various compounds. Okay, H3O plus, OH minus, H2SO4, H2 and so on. Can you guess which will be the conjugate acid or base of these pairs, this compound? For example, H3O plus, it is proton donor, so it will have a conjugate base. After donating proton, removing hydrogen, it will be H2O. So H2O will be a conjugate base of H3O plus acid. Or OH minus. Now OH minus will accept a proton, so it is a base. Okay, and after accepting proton will be again converted into water. So water and OH minus will be conjugate acid-base pairs of each other. H2SO4 will ionize to give H plus ion, proton donor, it's an acid. And after donation, we'll get HSO4 anion, and therefore H2SO4 and HSO4 minus will be conjugate acid-base pairs. H2O can donate a proton, can accept a proton, become a H3O plus or OH minus. So it will have both conjugate acid as well as conjugate base and so on. So if I check, these are the answers for this conjugate acid-base pair. And this is how you can guess a conjugate acid-base pair by just understanding the behavior of that particular ion or molecule. H3O plus, proton rich, will donate proton. After donation, will be converted into water. So this is conjugate acid-base pair. OH minus, it's electron rich, so will accept a proton and will be converted into H2O. So this is base and its conjugate acid. H2SO4, proton rich, will donate a proton, will be converted into anion, HSO4 minus. So it's a conjugate base of H2SO4. Cl minus will accept a proton, will be converted to HCl. So this is base and its conjugate acid, and so on. So this is what they have explained as a conjugate acid basis. Along with that, they also explain the behavior of water. In Arrhenius theory, water was a solvent and it had no much role to play. It was used only to dissolve acids or bases. But your Lowery Bronstead theory says that it can behave like acid as well as base. And such kind of molecule which can behave like acid as well as base is called as amphoteric. So water is amphoteric in nature. So let us take this example where acetic acid reacts with water to produce CH3CO minus ion and H3O plus. There should be a positive charge over here. So hydronium ion is formed, and then what you'll find that water has accepted a proton to get converted into hydronium ion. That means water is acting as a base. If I go to another reaction where H2O reacts with ammonia to produce OH minus and ammonium cation, you'll find that NH3 has accepted proton from H2O and H2O is converted into OH minus, a proton donor. Therefore, water acts as an acid in this particular reaction. So water acts as an acid when reacts with base. Water acts as a base when reacts with acid. So water can donate proton as well as accept proton, and therefore they call this behavior of water as an amphoteric nature of water. Now, this theory was very well accepted, and then another theory was introduced by Levis, which is called as Levis Theory of acids and bases, and this theory is also known as electron donor acceptor theory. Now, just like your Lowery Bronstead, which says proton donor acceptor, Levis theory says that acid is an electron acceptor, whereas base is electron donor. Or in other words, acid is electron deficient species, whereas base is electron rich species, which can donate electrons. Now, this particular definition can classify anything as acid and base, because and as well as all reactions can be classified as acid-base reactions according to Levis concept. Why? Because whenever say chemical reaction, either electrons are donated, accepted, shared. So every time we are talking about donation or acceptance of proton, and that is what is acid or base according to this theory. So if I want to explain this concept, I know that Levis acid will have electron deficient species, will have some empty orbital where electron can be accepted, and your base will have extra electrons. It is electron rich, which will donate its electrons to acid and produce a coordinate bond or a dative bond between acid and base. So a bonding pair will be now shared between A and B, that is acid and base. Now here are the some compounds like AlCl3, SO3, CO2. These compounds do not have hydrogen, do not have hydroxyl, they do not dissolve in water. So what you'll find that we cannot define them as acid or base by Arrhenius theory as well as by your Lowery and Bronstead theory. But it is observed that compounds like AlCl3, BF3, they are electron deficient. The aluminum in BF3 boron has 6 electrons in their outermost shell. So they are lack of one pair of electrons to complete their octet. Therefore, this particular compound, their central atom is electron deficient. They act as electron acceptor, and therefore such kind of compounds are called as Levis acids. Similarly, SO3, CO2 are not electron deficient, but the central atom like sulfur and carbon, they have 4 electrons in the outermost shell. So they can accept electrons, and therefore they become acidic in nature as per Levis theory of acids and bases. So such kind of compounds we were classifying as a neutral as per 2 theories what we had seen before. They can be acids as per Levis theory, and therefore they are called as Levis acids. So if I have a BF3, I have a ammonia, Ammonia, I know nitrogen has a lone pair of electron, and in BF3 just now we have discussed that it has 6 electrons in outermost shell and one empty orbital is there. Nitrogen can donate its electron to this empty orbital to form a coordinate bond with BF3, and this is how your acid-base reaction takes place. So NH3 becomes a Lewis base, whereas your BF3 or any boron compound becomes a Lewis acid to produce a dative bond, and the reaction will take place. So molecular orbital theory explains that you have two atoms out of which one is giving its empty orbital, other is giving its pair of electron, and a bond is formed between these two. That is called acid-base reaction as per Lewis concept. So by Lewis concept, all cations are Lewis acids, but all Lewis acids are not cations. Similarly, all anions are Lewis bases, but all bases are not anions. Take this example. Here SO3 is there, okay, and water is there. Water we know is electron rich because oxygen has two lone pairs of electrons and sulfur has empty d orbital which can accept these electrons very easily to form a dative bond. If it is formed, here water becomes acid and SO3 becomes your base because it has accepted the SO3 becomes acid and water becomes base. Water has given electrons, SO3 has accepted electron, so this is your acid and this is your base as per Lewis concept. Let us understand now that can we classify various things as acid and base as per Lewis concept. Let's take this example. Okay, methanol. It has oxygen which has two lone pair of electrons. So obviously it is electron rich, will donate electron and will act as a Lewis base. If I take SH minus ion, electron rich, obviously it will be a Lewis base. Ag plus, it's a cation, will accept electrons, so Lewis acid. H plus, Lewis acid. Cl minus, electron rich, Lewis base. SO3, now here sulfur has plus 2 charges, will accept electrons and therefore will act as acid, will act as a base. Ammonia has a nitrogen, lone pair of electrons, therefore electron rich, will donate electrons, act as a base. Water act as a base. CO2 accept electron, acid. So on, we can classify these compounds or ions as acids and bases. So as per this particular theory, there is always a coordinate covalent bond formation between acid and base. Lewis acid is a electron acceptor, Lewis base is electron donor. You can see here there is an extra pair of electrons which can be donated to this empty orbital of boron and form a dative bond. So in general, properties of acid, if I see their pH will be less than 7, they will convert blue in litmus into red, they are sour in taste, they have burning sensation, and they react with metals to produce hydrogen gas. The strength of acid is measured generally in the form of its pH, and pH, that is power of hydrogen, mathematically is expressed as negative logarithm of H plus ion concentration to the base 10. The pH scale has two parts, pH and pOH, which the relation between pH and pOH is given as pH plus pOH is equal to 14. This is something which we have already studied. So pH is a measure of H plus ion concentration in water. And so we are talking about Arrhenius acids. We are talking about their acidic strength. So if pH is 7, it is neutral, and if it is less than 7, it is acidic, more than 7, it is alkaline. And this is the pH scale which gives the relation between H plus ion concentration or H3O plus ion concentration and the pH of that particular solution. So we can classify compounds as acidic, alkaline or neutral based on